a local researcher from Cambridge who's going to tell us about renormalization approach to two-dimensional uniform spanning trees.
Okay, so first I would like to thank the organizers for the invitation to present my research. I feel very fortunate to work in Cambridge and to participate to the random geometry program. So my work, my presentation is the continuation of Wendelin's presentation last Monday. And it's a joint project with Stéphane Benoit and Wendelin Werner. And so my main goal is to rigorously complete the program which was outlined in Wendelin's Werner talk in the special case of the two-dimensional uniform spanning trees. And so let me just recall a bit the general picture. So we start with some graph here. So I took just a finite box of delta Z2. And then you let, on this graph, you run your favorite statistical model. So Wendelin presented the case of FK percolation last Monday. But you can also run percolation or the uniform spanning tree, which is what I will do today. And you perform an independent percolation of parameter alpha on this model. So you erase some edges with a probability alpha, basically. So all the blue edges which appears in this picture are removed from the picture. And then the question is, so you have a sort of perturbation of your model. For the case of the percolation, it's just it corresponds to do a percolation with a smaller parameter, but for the other models, it's something a bit different. And the question is, can you go backward, basically? So from this picture, where I remove all the blue edges, can I go back to the initial picture that I had here? And indeed, so you have to perform a computation to see that, but it's possible. And in fact, you can do it by sampling, so for the case of the FK percolation, another FK percolation with a different parameter P prime, and on a new graph where somehow the edges are concatenated. So this is something that Wendelin explained. And this is something that will also appear, in fact, for the uniform spanning tree, and that I will explain today. So this is just a picture that you can keep in mind. And let me just mention a few other things. So when you start from this picture and you perform a percolation, so of parameter alpha, you can imagine that alpha is going from 0, so where you have this picture, until 1, where you get this picture, right? And the goal is to understand the backward picture somehow. So when you go dynamically from this picture to this picture using those kind of figures. Okay, and we are interested in the case where the mesh of the lattice goes to 0. So when delta goes to 0, and also when in fact alpha won't be exactly, it will be dependent on this mesh size in fact. So we'll just be interested in the perturbation of this model which are very close somehow to this picture. So we won't remove too many edges from this picture. So it means that alpha is very close to 0. It goes to 0 with delta. And you see that if you started with a percolation model here, it corresponds somehow to the near critical percolation. Okay, so here is the outline of the talk. So first I will introduce a bit what we are doing thanks to the percolation model, because there are some issues that are similar in this case, and it's also a very interesting work. And then I will explain what we are doing on the uniform spanning tree. So I will introduce discrete dynamics and then what's happening in the continuum. So let me start with the percolation model. So you all know very well what is a percolation. So here I consider the percolation on the triangular lattice that I represent with hexagons and side percolations. And the mesh size is denoted by delta. And you know that there is a phase transition at p equals 1/2 for this particular lattice. And when p is smaller than 1/2, then you have only the gray clusters are very small, they are at a microscopic scale. And when p is greater than 1/2, on the other hand, you have an infinite unique gray clusters, and the gray clusters that do not belong to this infinite gray cluster are also of microscopic size. And what is the most interesting case is where p is exactly equal to 1/2, and then almost surely you have no infinite gray cluster. but you can find gray clusters of all size, basically. So there is no characteristic length in your model. And that's something that is quite typical for a critical model. And when delta goes to 0, you believe that your system will have a lot of symmetries. And in fact, it is conformal invariant. And so that's very symmetric. And let me just mention, so when delta goes to 0, there is an interesting question: is what is the interesting information that you would like to keep in your model? And as we are interested in the connectivity properties of our model, in fact, the natural topology that you would like to consider is the quad crossing topology, which was introduced by Schramm and Smirnov. And so basically, the information that you will keep is only about the quads. So the quads are some deformations of rectangles, and you wonder if there is an open path going from the left to the right. And you do that for all the quads that you can draw in your plane. And if you keep the information about all those quads, then it's called the quad crossing topology. So it's not exactly that, in fact, but it's the idea behind it. And another interesting question is what's happening when you don't take P exactly equal to PC, but P very close to PC. So, for example, P a bit smaller than PC. So, of course, if you take P a bit smaller than PC, even if it's very close, and then you let delta go to 0, you are in the subcritical regime. So there is nothing to say. So, in fact, to get closer to criticality, the idea is to take P going to PC at the same time as the mesh size of your lattice goes to 0. And so to understand what's happening, imagine that you start with P equals PC in a box of size 1, and with a very small mesh size delta. And imagine now that you slowly decrease P from PC. So it means that some gray hexagons will become white, but at the very beginning, when you switch only the colors of a few hexagons, nothing will happen, in fact, for your macroscopic crossing probabilities, so of this type. Because you see, basically, you will choose a point at random in this picture, and it will be in the middle of a cluster, and so it won't matter about the crossing probabilities. So if you look at a quad like this, and you wonder if it's crossed from left to right, then in fact, to change the state of this quad, you need to switch an important point, some special point in the lattice. And those points are called the pivotal points, and they correspond to, in fact, 4 arms points. So what are 4 arm points? It's points of this, which satisfy a configuration of this type. So it's in the middle of some here circle, and you have 4 arms which with alternating colors, like this. So gray arms, white, another gray, and then another white. And you see that if you have some configuration like this, in fact, the color of this point will become crucial for your macroscopic crossings. So you can see it, for example, in this picture. So here I've represented 2 gray clusters. Okay, so they are not they are separated at the time I consider, and so all those points here are 4 arm points, in fact. And if you switch the colors, if they are all white, and if you switch the color of one of them, which becomes gray, then you see that those 2 clusters will merge, and it will completely change. So a lot of the situation of a lot of quads in this picture. So you will be two large clusters will become a much larger one, and so you expect to see something different. To recap, so what I said is that if you change the color of some important points with some positive probability, then you expect to see a macroscopic difference with the critical regime, and that will be the near critical regime. But let me just say that if you switch the color of an infinite number of them, of too many of them, then you expect to be too far away from criticality. So you really have to understand quite well the rate at which you have to change those pivotal points. So it's important to know the number of pivotal points in a box of size 1, and you see that it corresponds roughly to this quantity. So you have delta at the power minus 2 points in the box of size 1 and the probability that you have 4 arms of macroscopic size. And case 10 proved in 81 that indeed near criticality is governed only by those 4 arm points. So if you take P equals to PC and something which is of the order of magnitude of this quantity here, then you are in the near critical window. And so it's important to understand how this probability decreases with delta. And in fact, it was computed by Loller, Schramm, Smirnov, and Werner in 2001. They proved that it decreases like delta at the power 5/4, plus some correction in the exponent here, thanks to SLE techniques. Okay, so another question. So I defined where is near criticality, but you see that to introduce that, I in fact introduced a dynamical model. And somehow it's useful, in fact, to consider a dynamical model because it will explain to you how the criticality arises from near criticality. And so you want something like you start, for example, with the critical system and you switch the gray hexagons to white when the time increases. And for percolation, this has been studied in a remarkable series of papers by Garban, Peter, and Schramm. And one of their results is that if you take the percolation of a parameter, P, which is equal to PC at the initial time, lambda equals 0, and then it decreases from exactly the correct factors that I gave you here, so that you are at time lambda, you are in the near critical regime, then it converges in distribution towards a continuum object when the mesh size delta goes to 0. And it converges for the score code topology on CAD-like processes in the Schramm-Smirnov space, so where you keep the information about all the quads in your picture. And what is interesting is that, in fact, you can construct this process directly in the continuum. So, in fact, if I give you the continuum percolation, here, critical percolation, so I start with the continuum version of the critical percolation, and then you can perform a Poisson point process of intensity lambda on the pivotal points that you have in your in the continuum, and then it will give you indeed the construction of this process. And but of course it's not so simple because the pivotal points, the measure on pivotal points, it's not nice, and so in fact you need a cutoff to make sense of this. And instead of looking at all the pivotal points, you will look at all the pivotal points which have an importance greater than epsilon. And then you have to show that indeed when epsilon goes to 0, it converges then. And to prove this convergence, there are several issues. So it's a very difficult result, very technical, and also very deep. So, so first, there are some issues because the Schramm-Smirnov topology is not so nice. So you have to prove that 4 arms events are measurable, for example. But that's not the main issue. The main issue is that you can create new pivotal points when you do this procedure. So you see that when you start, so I said that to construct this continuum version, this continuum process here, I just use the pivotal points at the starting time. But what's happening is that when you switch the color of some hexagons, you will create new pivotal points. And it will really happen. So it's quite easy to create new pivotal points, and you will create many of them. But thanks to, something nice is that you don't create too many of them. So in fact, the probability that then your Poisson point process of intensity lambda chooses one of those new pivotal points is negligible. So, but they have to prove something very deep to be able to do that. And it's a sort of a stability result. So they constructed indeed this continuum percolation, and they also derived some properties about it. One of the nice properties is that it is conformally covariant. So you see that when you are at criticality, you are conformally invariant. And when you are at near criticality, you lose some of the symmetry, but you are still quite symmetric. You are conformally covariant. They also prove that this process is Markovian. which is not obvious. I mean, in the discrete setting, it's obvious that it's Markovian. But it could occur that in the continuum, you lose some information and you are not Markovian anymore. So indeed, this continuum process is also Markovian. Okay, so let me now talk about uniform spanning trees. And so I just recall very briefly the uniform spanning tree model. So if you take G a finite connected graph, the uniform spanning tree is simply the uniform law over all the spanning trees that you can draw on your graph here. So spanning means it spans all the vertices, and a tree is connected and without loops. Okay, so here I've drawn an example of a spanning tree. And by definition, you see that if I take two vertices in my x and y in my graph, I have a unique path in the uniform spanning tree between x and y. And we can also extend this definition by adding weights on the graph here. So if my edges have weights, then I can sample not a uniform spanning tree, but a weighted spanning tree. And in fact, so the probability to choose a spanning tree will be proportional to the product of all the weights that of the edges that it uses. And so this is for finite graphs. And when your graph is infinite, you just have to take an exhaustion by finite connected subgraphs. And it's possible to prove that the law of the uniform spanning tree converges in all finite windows. So you will get what we call a free spanning forest in your infinite graph. So here I represented what's happening for finite box of Z2 and when you increase the box. And you see that it's called a forest here because the limiting object has indeed no loops by definition, but it can have many connected components. But for the case of Z2 that we will consider today, the limiting object is indeed a tree. Let me just mention a last thing about the uniform spanning tree is that if you draw a uniform spanning tree on, let's say, a finite box of Z2 here, you can draw its dual on its dual graph, so like in this way here. And it will also have the law of uniform spanning tree, except you have to change the boundary conditions. So here I started with 3 boundary conditions, and it becomes a wired boundary conditions for the dual graph. So typically, how do you do to sample a uniform spanning tree? So the most important tool is the Wilson algorithm, and it uses loop arrays random walks, which were introduced by Laure in 80. And so loop arrays random walk is simply you take a simple random walk, starting at some point until it exits some domain, and you erase all its circles so that you will have indeed a simple path. And Pimentel in 81 proves that if you take 2 points in your graph in the uniform, then the branch in the uniform spanning tree between x and y has the law of a loop array random walk starting at x until the first hitting time of y. And Wilson, in fact, generalized this procedure. So here you have the law of only one branch of the uniform spanning tree. But if you take another point, in fact, the law of the branch that you see appearing here is simply the law of a loop array random walk independent of the first one until it hits the first one. And you can do that for all the points in the graph, all the vertices in the graph, and you will get a spanning tree by definition, and in fact it has the law of the uniform spanning tree. So this is the Wilson algorithm, and it's great not only to generate a uniform spanning tree, but also to get a lot of information about the uniform spanning tree. Okay, so now we have a uniform spanning tree on some lattice, and we want to take a mesh size on this lattice and to let the mesh size goes to 0. So let me just say that the uniform spanning tree, even if it's not obvious because there is no parameter in the system, it has the properties of a critical system. So for example, you can see that there is no characteristic length in for the uniform spanning tree model. And if you take a uniform spanning tree on delta Z2, what is the limit when delta goes to 0? So of course, you have to specify a good framework for which you would like to take the limit, because if you just consider, for example, uniform spanning tree as a subset of the plane, then it wouldn't be very interesting. It just converges to the whole plane. So you have one possibility, which is quite common for random trees, is to look at the contour of the uniform spanning tree. And it was proved by Laure, Schramm, and Werner that the scaling limit of this path, which goes along the contour of the tree, is conformally invariant and is SLE8. But we will see that in a moment that, in fact, we use another topology which will be more suitable for what we are doing. So let me now introduce the model that we are considering around the uniform spanning tree. So we consider a dynamics where at time t equals 0, we start with a uniform spanning tree on delta z2. And keep in mind that we will be always interested in the limit delta goes to 0. And we define a coupling of spanning forests such that so at time t equals 0, you start with a uniform spanning tree. And when the time increases, you will erase edges in an independent Poissonian way. So it means that each edge will carry a clock of a certain mean that I call m delta, and which depends on the mesh size delta, and will be removed when the clock rings. So here I represented a picture at time t equals 1 of what we could get. So here is this uniform spanning tree, and all the red edges that appear here are removed by the Poissonian procedure. And you see that when you remove an edge from a uniform spanning tree, in fact, each time you remove an edge, you create a new cluster, a new connected component. And so you will get many connected components at this time, and they are represented on the right-hand side. And you see that it really corresponds to this picture, because when I remove this edge here, I create this small square, which is represented on the right here. And notice that all those clusters that appear are in fact, when you remove an edge in the discrete setting in the uniform spanning tree, it's as if you were adding an edge in the dual uniform spanning tree. And so these are all the cycles that you get in the dual uniform spanning tree at this time. And so it's quite interesting. So what you have to keep in mind is that all those boundaries, in fact, can be seen in the dual graph as a circle of the dual graph. So in particular, they are part of loop arrays random walks. They have the law of loop arrays random walks. So here, so I have drawn a movie about simulation about what's happening. So you see a fragmentation of the plane and into many and many clusters. So this is my small contribution to what you can show to your mom for the, yeah, okay. And let me just now talk about, before going to the scaling limit, talk about the backward discrete dynamics. So in fact, the question is the following. If I give you the forest at a fixed time, capital T, then can you reconstruct the law of the backward movie until you get back the uniform spanning tree at time t, at the initial time t equals 0? And if it's true, then it would mean that the backward dynamics is also Markovian. And indeed, you can see that it's obviously true, because so you have to connect all those clusters, right? And you have to do it in such a way that you don't create cycles, because you don't want cycles in your picture here. And so, in fact, it's easy to see that all the proper way to do it will have the same probability. So you just have to choose one of those possibilities uniformly with a uniform law, and then to add edges in a proper way, so that I mean with a Poissonian, with exponential clocks, and you reconstruct your backward movie. So indeed, your backward dynamics is Markovian. It's just a small computation. But in fact, we have another idea to see more in another way that this backward dynamics is Markovian, in a more intuitive way. Our idea is to associate to the forest a weighted graph, and where the vertices will be the connected components, the edges will be between the neighboring connected components, and you will put weights on the edges. So the weight of one edge is simply the length, the common frontier between the two vertices that you are linking. So here I represented, and I call this graph here, this weighted graph, the structure graph of my forest. So here I represented a part of this structure graph on this picture. So you see that indeed each cluster, each color here is associated to one vertex, and I put edges when I can between the neighboring vertices, and the numbers that appears here corresponds to the length of the frontiers. And now if you sample a weighted uniform spanning tree, so you see that so you lose a lot of information when you do that. Basically you lose all the geometry, everything. You just have this weighted graph which is associated to this forest. Now if you sample a weighted uniform spanning tree on this structure graph, then you can reconstruct the law of the backward mu v using this weighted uniform spanning tree. So in fact it's easy to see that so you will select some edges in this way using the weighted uniform spanning tree, and if you reconnect your forest using those edges and in a good way, then you will have the law of backward mu v. Okay, so now let me talk about how do we go to the continuum. So the first question is that, so recall that we remove edges using exponential clocks of a certain mean m delta that I didn't specify for now. And the question is, what is a good speed for erasing edges when delta goes to 0 to get a non-trivial object? And indeed, it's the right question. In percolation, we have seen that we had to remove, to change the color of some points, and what was important is the pivotal points, to be sure that we hit some of them with positive probability. So the 4 arms points played the crucial role here. And in the uniform spanning tree, what plays the role of those pivotal points are in fact the important edges are the one which belongs to the macroscopic branches that you have in your tree. So you see here I have drawn this uniform spanning tree on a finite box, and I have drawn a long, what I would say is a long branch here. And if I cut this branch in the middle, you see that I will create a very large cluster, so I will see something at the limit. So we have to understand what's happening for the branches of the tree when delta goes to 0, because we want to understand, in fact, the length of those long macroscopic branches when delta goes to 0. So recall that the branches in the uniform spanning tree are distributed like loop arrays under Moore, and in fact we have a theorem which says that the loop arrays under Moore, the scaling limit of the loop arrays under Moore exists and is SLE2, which is a fractal curve of dimension 5/4, Hausdorff dimension 5/4, which was proved by Vincent Beffara. And so they proved this, that this scaling limit exists, but only for a particular parameterization of the path by the capacity, so namely by the size of the compact sets that you create. So it's not the parameterization by the length of the walk, but only by its capacity. So, as we are interested by the length of those loop arrays under Moore, we need some stronger results. And in fact, there have been results about it recently by Lawler and Benesch, Wicklund, and Lawler. They said that the macroscopic branches of the uniform spanning tree, so in fact, so the loop arrays under Moore, have a typical length delta at the power -5/4. And so in fact, the 5/4 shouldn't surprise you, because I told you that SLE2 has a Hausdorff dimension 5/4, sorry. And but it's a very strong result, in fact, and it's because they proved it not only logarithmically, but up to a constant. So it's a very strong result. And so we have a very precise information about the macroscopic branches of the uniform spanning tree. And so, so in fact, if we hit one of those macroscopic branches, then we know that we will modify something important. And you see that there are much less important edges. So there are about delta at the power -5/4 important edges in the uniform spanning tree. And you have to compare this to the number of the edges in the uniform spanning tree, which is delta at the power minus 2. And so you see that if you just pick an edge at random in a uniform spanning tree like this, you will be, in fact, very close to a leaf and not in a macroscopic branch. But so for us, it gives us the correct speed for our model, which should be delta at the power 5/4. We have also, we expect to have soon, in fact, a stronger result about the convergence of the loop horizontal walk towards SLE2. So not for this capacity parametrization, but for its natural parametrization. And so if you take the loop horizontal walk that you renormalize by its length, then it will converge to SLE2 for the natural parametrization. So what is the natural parametrization of the SLE2? It's given in terms of the 5/4 Minkowski content of the curve. So basically what you have to remember is that if you indeed rescale this loop horizontal walk in the good way by its length, then it converges towards something. And we will rely on this result. So yes, I didn't mention, but it's a result that should be proved by Lola and Wiklund soon. And we will rely, in fact, on this result for the construction of your continuum model. Okay, so let me explain what's happening in the continuum now. So what are the natural questions here? So first, if we take our cutting process, does it converge towards some object, like we have seen for percolation model? And so we have, as for percolation, we have to specify a good framework in which we'd like to consider the limit. And then the second question is about this backward dynamics. So is it still Markovian at the limit in the continuum? And can we describe it thanks to a continuum structure graph? So let's first see the convergence for the time t equals 0. So I told you that we can take, for example, for the full scaling limit of the uniform spanning tree, the contour of the tree, for example, which converges towards SLE8. But here we will choose a framework of Schramm, which was introduced in 2000, where in fact we keep the information about all the branches in our tree. So here it's a union over all A, B. So A is the starting point of the branch, B is the ending point, and gamma AB is the branch that you have between A and B. There is a unique path, in fact, and so you keep this information. If it exists, of course. If you have no branch between A and B, then you don't have a triplet of this form. So you see that indeed our discrete trees can be encoded in this way, and the continuum tree will be encoded by those branches tree. And we put the Hausdorff topology on this set. And it was proved by indeed that the uniform spanning tree scaling limit exists in this framework. And so we can denote G of 0, the limit of or the starting point of our process, G delta of 0. There is a crucial property about this continuum uniform spanning tree, is that it's a finiteness property which was used by Schramm in 2000, in fact, which basically says the following, that if you take a set of dense points in the plane, countable dense planes, then you can generate a finite subtree using the first n points of this countable dense set of points. And you see you can do that. So let's look at the finite subtree generated by those n points, and you view that in the Schramm space. Then in fact you can prove that it converges in distribution towards the continuum object, the continuum uniform spanning tree. And so it's a very nice result, and because you see that we can generate the finite subtrees simply by using the continuum analogous of Wilson algorithm with instead of using loop horizontal walk, you will use SLE2 processes. And so thanks to this result, and also thanks to the convergence, the conjecture about the convergence of loop horizontal walk towards SLE2 for the parametrization, we can prove that indeed our discrete object converges towards a continuum process in fact, that we can describe directly in the continuum, just by cutting the continuous branches. So what are the nice property of this process at the continuum? So first, and it's something that is direct from our definition, our process is self-similar. So it means that if I give you the movie, and now I zoom on the movie by a factor 2, then in distribution, you will see exactly the same thing as if I slow down my movie, the initial movie, by a factor 2 at the power 5/4. So it's something that just comes from the definition. In fact, you can prove even more. You can prove that this process is conformally covariant. And what is more interesting is that so we have a continuum object like this, and we would like to understand what's happening for the backward dynamics. So is it indeed Markovian, like we have seen in the discrete setting? So if you fix some time, capital T, and I give you the forest at time capital T, can we reconstruct the dynamics in the time interval 0t? So recall that in the discrete setting, we were using a weighted uniform spanning tree on some structure graph that enables us to reconstruct the dynamics in this time. Yeah, I should have also mentioned that this, in fact, I didn't say, but this backward dynamics is quite natural on its own. I mean, I could have also described my process by just using this backward dynamics, because when you want to sample a uniform spanning tree, what you can do is that, so you have your finite box, and you sample a whole uniform spanning tree, and you choose one of on the edge on this picture, and so then you put it, and then you have a new graph with one edge. You coalesce this edge so that it becomes just one vertex, and you have a new structure graph here, and a new graph, and you can sample another uniform spanning tree on it, and etc., and continue this procedure. So it was something quite natural, in fact, even in the discrete setting. But anyway, so is there a way to make sense of this procedure in the continuum? And for that, we can define, in fact, a continuum structure graph, where the vertices are a connected component of so there is no trunk here, of the forest that you have at capital T. And the edges you put edges like before between the neighboring connected components, and you put weights which are proportional to the 5/4 dimensional length of the surface of contact. So you have some continuum analogous of this structure graph here. And so to prove the Markovian property of the backward process, we would like to show that the discrete weighted uniform spanning tree on the discrete structure graph that we define converges towards the weighted free spanning forest on this continuum structure graph. And so we have to establish, in fact, the convergence of those structure graphs. And here there are some difficulties. So because this structure graph, you will see at the limit delta goes to 0 will become not a very nice object. In fact, if you take, for example, two connected components, like for example here the green one and the purple one, between the two, and which are neighbors here, you can see. In fact, between the two of them, there will be an infinite number of a small cluster here between that you could use to pass from this connected component to the other one. So they will have an infinite number of neighbors here, common neighbors, those two connected components. And so we have to prove, in fact, that the contribution of the small clusters that you have in your picture is negligible. And to do that, so I've drawn a very sketchy proof. If you have two connected components, here they are separated, in fact, by a branch of the dual tree here. So I represented the branch of the dual tree. Here it's our primal tree, so the uniform spanning tree that you cut. And all those points here are the points that you cut that you have cut at this time. So so you see that you create clusters, and you want to understand from going to this this connected component to this other one. You have all those clusters that annoys you, and you would like to prove that the contribution of the small loops that you get here is negligible. And to do that, the tools that we are using is that, in fact, we are all those blue paths here are branches in the dual tree. And so we know their distribution and everything. And so we can see a small cluster in this way. So here I have drawn several circles. So it's just to say that, in fact, a loop can be detected by looking at arms events in the uniform spanning tree. So here you have two arms events in this small circle, and then another two arms events in this annulus. And we can control, in fact, arms events, like it's done for the percolation. I mean, we have information about that in the uniform spanning tree. So we have estimates which permits to deal with such a picture. So of course there are some, I mean, I didn't say everything because in the uniform spanning tree there is no independence between disjoint part of the plan. So you have to so you have to prove something. But it's a bit the idea behind the proof that small clusters is negligible. Okay, so let me now conclude. So we're able to construct near-critical dynamics, what we can call a near-critical dynamics, around the planar uniform spanning tree. We can construct it directly in the continuum, and using those nice weighted graphs that somehow remove a lot of geometric information from the picture. And using the Markovian property, we can have an invariant measure on forests and give some sense of the renormalization group arguments that are used by physicists. And so, as said Wendelin, the plan would be maybe to extend this approach to other statistical models like FK percolation, and I mean, in a much longer term, I guess, to higher dimensions, because so for the moment, of course, we have no tools to deal with higher dimensions. Okay, thank you for your attention.
What did you mean by the continuum analog of Wilson's algorithm with SLE2 processes?
I just mean that so you have your finite points, and then you draw a SLE2 process from one point to the other, and then another SLE2 independent SLE2 process starting for the third point, etc. Yes, so okay, you have to define what is a loop SLE2 process between 2 points.
How do you do that?
So I guess what you could do is first define an infinite SLE2 process, and then draw the other one, the other part, and then link the two of them.
Yeah.
So start with uniform spanning tree. You can
Could you shout, please?
start with uniform spanning tree. You can use this dynamics to take off edges and glue edges. So, do you know if that's noise stable? I mean, they were.
Well, what do you mean by that?
Well, there was studies in terms of percolation. For instance, view them as a Boolean function, 0 to 1, and looking at some
Yes, so
microscopic problems.
I don't know.
What's that?
The uniform spanning tree is sort of, I mean, it's not just I mean, it's very dependent, so, I mean, you can't view it really as a Boolean thing with Boolean input. And
But you could take the stacks in Wilson's algorithm and resample the stacks.
yeah, but then
Different.
Anything else? Well, thank you once again, Laurie, for a nicely illustrated and clear talk. We resume here.